Okay. Hi guys, so in this lecture we'll be continuing on seeing the geometrical isomerism in case of cumulene. So as I mentioned in the previous lecture that uh, the smallest cumulene is a three-member ring, three-member chain uh, with double bonds on uh, all the three carbon atoms. So this is known as alene. Okay. So let us take an example and let me explain you the points that I made in the last lecture, that if the number of pi bonds are even in case of cumulene, then terminal carbon valency lie in perpendicular plane and it will not show geometrical isomerism. So let me explain more into that. So let's say I have this compound. Now it contains even number of pi bonds. Okay. Now as you can see that this, let's suppose this lies in horizontal plane, then for the double bond between this carbon atom and this carbon atom, this will lie in perpendicular plane. Okay. And for the same, if this lies in perpendicular plane, this would be actually in the upper half of this perpendicular plane, this CS3 group, and this H would be in lower quadrant or lower half of the horizontal plane. Okay. So if this was the horizontal plane in which these two carbon atoms are lying, this was the horizontal plane, and this is the horizontal plane in which it's the same horizontal plane in which these two groups are also lying, then these two groups are actually above the horizontal line and this is below the horizontal line. Okay. Why? Because this pi bond lies in perpendicular plane to this horizontal plane. Okay. So this CS3 and this H lies in the air. Okay. So if you compare the distance L1 and L2, they will not change, because if something is in parallel plane, this is a horizontal, you can say X plane, and this CS3 and H actually lies in Z plane, or there is a distance, you can imagine that it is in the air. Okay. Minus Z plane. Okay. Now here in the X plane we have CS3 and H attached here. Now even if we change the positions of H and CS3, the aerial distance is not going to change. The aerial distance for this CS3 and this CS3 was L1 here, and now even if we change the positions of CS3 and H, so let's suppose CS3 comes here and H goes there, even then the aerial distance is not going to change, because it is still going to be the same. Why? Because this is in the horizontal plane and this lies in the air. Okay. So for this case there will be no geometrical isomerism. Okay. And when I say in case when we have even number or odd number of pi bonds, so what will happen is, if there are odd number of pi bonds in cumulene, then the terminal carbon valency lies in the same plane and it can show geometrical isomerism. So what will happen in this case is, for example, these two are in one plane, hence these two pi bonds will be in perpendicular plane. Then these two carbon atoms will be in perpendicular plane to this plane, so perpendicular plane to this plane would be again horizontal plane. So if so, this implies that this double bond and this double bond lies in the same plane. Hence, this CH3H and this CH3H lies in the same plane. Okay, so now as this CH3's H and this CH3H lies in the same plane, when we interchange the positions of H and CH3, the aerial distance would eventually change. In this case, it would be this one, and if we change the position of CH3 to here and H to here, this would be L2. So L2 would be greater than L1. Let me rewrite it. L2 would be greater than L1. Hence, there would be geometrical isomerism in this case. There would be no geometrical isomerism when there are even number of pi bonds. Okay, so I hope you get the explanation. So what if we have this compound? Will it show geometrical isomerism? Yes. Why? Because there are even number of pi bonds, 1, 2 and 3. Hence these and these lies in same plane. Okay, now let us see for this compound whether this cumulene will get involved in geometrical isomerism or not. No, because this contains even number of pi bonds, and if we see that if this double bond lies in a horizontal plane, this double bond will lie in perpendicular plane, which may be a z plane, and in that case this CH3 and H will be in the air and this CH3 will be in the same plane. Hence because there is different perpendicular planes for this CH3 and H, even if we change the position of this CH3 and H, the aerial distance is not going to change. Hence it will not show geometrical isomerism. Okay, so let's see this example, whether this will be involved in geometrical isomerism. And we have H and CH3. Okay, so you know that if this is a sp3 hybridized carbon atom, and as you can see that this is a double bond, so it will lie in one plane. This ring and this along with this carbon will lie in one plane, and you can say that these also lie in the same plane. The CH3 and H groups attached to this carbon atom will lie in the same plane. But when you say that this is a sp3 hybridized carbon atom, then the bond angle would be 109 degree between its groups or substituents attached to this carbon atom. So due to which, if this ring is in the same plane, so you know the tetrahedral structure, right? So for this carbon atom, if we just rotate it and make it like this was the ring in which that we are talking about this carbon atom, then one would be below the plane and one would be above the plane. Okay, so this carbon atom, we can say that it is above the plane. I can actually redraw it with showing the actual above the plane and below the plane with dash and more brighter bond. So this is in the air and this is perpendicular to the plane in which these CH3 and H groups are. Hence the aerial distance are not going to be changed even if we replace it. Even if we change the positions of this CH3 and H, even if we do something like that, then also the aerial distance with this CH3 will not change. Why? Because this is in the perpendicular plane. Hence it will not show geometrical isomerism. Okay, next we will look into the EZ configuration. So what is EZ configuration? I think I have mentioned that EZ configuration in some previous lecture in some one or two examples. We will see this in detail here. So E stands for integer and Z stands for Zusammen. Okay, so integer means on bulky groups on opposite side, and Zusammen means same side. Okay, so just write it like this: atomic masses on same side is called, I beg your pardon, Z, and atomic masses on different side is called E. Okay, so let us look at this by an example. We have something like a lone pair here and a BR here. So in this case, this is the bulky group, and in this case, this is the bulky group. So this is Z configuration. Okay, so one more point here is that you might answer that what is the mass of lone pair. So just for the sake, lone pair mass can be considered 0. Okay, let us look into this example. So priority on the same priority is at priority on the basis of atomic number, atomic mass. Okay, so high atomic number is given high priority. So let me write it like this: high atomic number is given high priority. So we are talking about Ez on basis of same atomic mass. On Z priority on the basis of atomic number. Okay, so I'll give you an example as to where we need to see this priority rule. So in case of isotopes, priority on the basis of atomic mass. Hence, T's priority would be greater than D and then H, and obviously O18H would be given more priority than OH. And obviously second point is lone pair is given lowest priority because its mass is 0. Atomic mass can be considered 0. Okay, so with this we come to the end of this lecture, and from the next lectures we'll be seeing more on the EZ priorities, and we'll be practicing more on EZ configurations. Okay, till then, good luck and goodbye.